you can get the recording and share it with your colleagues. I'm hoping that next week, they'll be back on the platform because I'll be starting a new topic, and that will be Doppler ultrasound. So we cannot use Google Meet because it is challenging when you are presenting, because demonstrating and even drawing things on Google Meet challenges so much, and also Zoom, I don't have a licensed Zoom, so that implies that every 40 minutes that pass, it will be closing us off, which I don't like. So let's have this last bit of artifacts. We will share with the rest of the members that are not in position to access the platform right now. So today, let us look at attenuation artifacts. You know what attenuation means? It's an English word. And from the things that we have said since the beginning, attenuation means reduction in energy or reduction in intensity of the beam as it is passing through an object or tissues. So the first artifact is called shadowing, just like the way you hear the word shadowing. When you stand in the sun and you block the sun rays, you see a shadow behind you or anywhere which is opposite to the direction of the sun. So even here, with shadowing in ultrasound, whenever the beam encounters something which blocks it, something which reflects it, something which absorbs it, then that object which absorbs or reflects will cast a shadow on the structures which are behind it, because it has absorbed this beam and nothing is left to interrogate the structures beyond beyond that structure. So you will see a shadow casted on those structures after a high attenuating structure. So shadowing is the reduction in the echo amplitude from reflectors that lie behind a strongly reflecting or attenuating structure. So a strongly attenuating or reflecting structure weakens the sound distal to it, causing echoes from the distal region to be weak, or even causing no echoes from the distal regions, and thus to appear dark like a shadow. So if we look at okay, before we look at the image, so if for example you have a structure here and this beam comes to it, this is a highly reflecting or attenuating structure. Most of it is going to be reflected back, and some of it that goes into this structure end up getting more and more absorbed in the same structure. And even if there is something that is left to interrogate the structures below, remember the structures below, they also have to create echoes which have to come back. But remember, these echoes must also go through this high attenuating structure, weakening them even more. So you realize that you have no echoes that are actually arising from the structures below this. So this structure is going to cast a shadow on the structures below. So all this area will appear black, like nothing is there. So shadowing is created by high attenuating structures. For example, bones, stones. They are giving you here the stiff breast lesions. They can all create these shadows. Here they are showing you different structures of different sizes and the shadows they create. If the beam encounters a large, strong reflector, it will cast a very dark shadow. If it encounters a large, strong reflector, it casts a very dark shadow. If it encounters a small, strong reflector, it will cast a shadow, but it will not be as dark as that results from the large one. If it encounters a small, weak reflector, this weak reflector will cast a very small shadow that you have to be observant to see it. Like, for example, very small stones which are in just formation. They are small and weak reflectors, but they cast small shadows that you have to be observant to see them. For example, stones which are forming in the gallbladder, in the kidney, maybe in the urinary bladder, and they are small. You have to be very observant to see them. So here we have examples. A shadowing. In A, we have a shadowing from a high attenuation calcified plaque in the blood vessel. Here in the common carotid artery, casting this shadow. You see it is here and casting a dark shadow. Then in B, we have a stiff breast lesion causing this shadow. C to F, we have other examples of shadowing. So in C, you'll see the shadows originating from the vertebral bones, here, there. Those are vertebral bones. This is a kidney here, and this is a liver here. So these are vertebral bones below. So they are casting those shadows. So those are some of the examples of shadowing. So shadowing artifact is a very useful artifact. Of course, sometimes it can be a problem, and maybe when something is casting a shadow on the area of interest or on the tissue of interest, then the shadowing becomes a problem. But it is useful. For example, it can be used to assess stones, because without shadows, you can't see the stones in the bladders and maybe the kidneys. You can't see those stones because they must produce these shadows for you to see them properly. If, for example, they were not in position to produce shadows, then you would not even see them. They will blend in with the fluid in these bladders, and you don't see them. But because of their acoustic impedances, they are being highly attenuating, they are being highly reflecting, they will cast a shadow that will show that something is blocking the beam, and that could be a stone there. But in case you don't want it, there is a solution to it. You can use what we call spatial compounding, whereby if you have that structure here and you have a transducer here, this, for example, linear probe, which we know that it only produces beams that go vertically downwards. So of course, these beams, they will cast a shadow like that. This all will be a shadow. But for the spatial compounding, the transducer will be made in such a way that it sends beam also in other directions like that. This is what we call steering of the beam, and also steers them on another side like that. So you realize that some of the beams will go around the structure to reveal the structures which were initially in the shadows. These beams that go around the structure, they interrogate the structures below below this attenuating structure and reveal those structures below it. So that is what we call spatial compounding, steering the beams in various directions such that the structures which were initially in the shadows can be revealed. So that is shadowing. Then we go to another artifact which is called comet tails. Comet tails. A comet tail is an artifact falling in the family of reverberation. It's a reverberation artifact. The comet tail, just like the way you hear the word comet, comets, they are found in space. They are those large stones that keep wandering about in space, moving at very high speeds. Most of you have seen them, just that you don't know them. I know most of you know what they call chibunum or meteorite. So that chibunum, that thing that you call chibunum or meteorite, those are just larger stones in space. You're able to see it because whenever that stone enters into any planet's atmosphere, if it enters into any planet's atmosphere, because of its high speed at moving, the friction between this stone and the Earth's atmosphere makes it to catch fire. The friction between that large stone or that large comet and the Earth's atmosphere makes it to catch fire. Just like when the astronauts are returning back to Earth from space, their capsule, when it is re-entering into the atmosphere of the Earth, it catches fire. I think you have heard about this. It catches fire because it is at a very, very high speed as it is re-entering the atmosphere. Until when its speed reduces, that is when that fire disappears. So anything that is moving at a very high speed in the Earth's atmosphere catches fire, or in any planet's atmosphere catches fire. So when you're looking at this chimonomu, there is a tail that it leaves behind, a bright tail. That's all fire. It's a tail of fire. So that's why it is called a comet tail. So looking at this artifact in ultrasound, it looks exactly like a comet tail. But it is as a result of reverberation. Reverberation is when the beam undergoes multiple reflections between highly reflecting interfaces. The reverberation that we saw last time in propagation artifacts, it is as a result of multiple reflections between large, highly reflecting interfaces. Large, highly reflecting interfaces. This one, it is produced when there is multiple reflections between very, very small, highly reflecting interfaces, which are so close together, which are very, very close together. So it produces these multiple structures, repeated structures below the point of formation, but with a comet tail, you may not see those repetitions. Yes, the structures have been repeated, but because they are so close together, your eyes may not see that these echoes have been repeated many times. For you, you see just a tail. So this is what I'm talking about. You see, these, they look like waterfalls from a very high mountain, but it looks like a comet tail. You see them, those ones, like this one here. There's another one there. So for you, you see a signal coming from a certain point and then it goes down. It also reduces in the brightness. And if you were to magnify this image, if the system was to magnify this image to thousands of times, you would see that these echoes are just repeated downwards. So science says that this artifact is useful. And indeed it is useful, but you can find out from the sonographers, this experienced one, how useful it is, because it is also it is also used in diagnosis. For example, if they are scanning a gallbladder and these comet tails are visualized when they are coming, from the wall of the gallbladder, it signifies something, which I'm not sure of because I'm not a sonographer, but it signifies something which is not good. I don't know what would have happened to the wall of the gallbladder. Maseleka, are you saying something?
It signifies ulcerations, like someone with gastritis. That's how normally the wall looks.
Okay. So other things you can find out from the experience sonographers, but yes, it signifies something not right about the wall of the bladder. So it doesn't only happen in the bladder, but it can also happen somewhere else. So maybe it could also be signifying something in other areas where it is formed. Okay, so that is a comet tail. It's a reverberation artifact, and it is as a result of multiple reflections between small, highly reflecting structures which are very close together. So they form those comet tails. Then we have what we call ring down artifacts. These are almost similar to the comet tails, but for them, they are produced by gas bubbles only. Where there is gas, most likely there will be ring down artifacts. And they also form those signals that look like comet tails. But this is as a result of the beam getting trapped in these gas bubbles. These gas bubbles vibrate. They vibrate and then produce their own signals. I repeat, the beam gets trapped in the gas bubbles, and when it gets trapped, these gas bubbles vibrate or they resonate. And when they resonate, they instead produce their own signals. So which will go back to the transducer, and then the transducer will show them as continuous signals originating from somewhere where there's gas downwards, almost to almost the bottom of the image. So these ring down artifacts, in most cases, they don't even lose brightness. They can be bright from the point of formation to almost the end of the image. Whereas comet tail, their brightness reduces downwards because remember, they are reverberation artifacts. The brightness reduces downwards. But sometimes ring down, they may not fade in brightness. They can be so bright from the point of formation to the bottom of the image. So you see them here. This one, okay, it's not good enough. Do I have some other images? I don't have. But you can Google up some of the ring down artifacts. You see them on Google, and then you realize that whenever they show you this image showing ring down artifacts, there is gas somewhere which is causing them. So you normally see them around the pleural line because of the lung tissue that is having some gas bubbles. You see them around the lung. You see them in the bowels, which have gases, and anywhere else where you can find gas, you can see these ring down artifacts. Then we have another artifact which is called acoustic enhancement. This is the opposite of shadowing. The opposite of shadowing. Shadowing is created by a highly attenuating structure. Acoustic enhancement is created by a low attenuating structure. Where you see a dark shadow in shadowing, here you will see a bright shadow. Is it even called a shadow? You see bright area instead. So here you see an increase in echo amplitude behind a weakly attenuating structure. For example, behind a fluid-filled cyst. And it's a very useful artifact, especially when you're assessing fluid-filled structures. Just like shadowing is useful when you are assessing highly attenuating structures like stones. Here, you use it to assess fluid-filled structures. Shadowing and enhancement result in reflectors being displayed on the image with the amplitudes that are too low, that is with shadowing, and too high, that is with acoustic enhancement. In most cases, it is referred to as posterior acoustic enhancement. The attenuation rate of the structure is lower than the surrounding tissues. For example, the cyst. The attenuation rate of the cyst is lower than the surrounding tissues. A mostly useful artifact to help identify fluid-filled structures. It is acoustic enhancement is the strengthening of echoes distal to a weakly attenuating structure. Here we have low attenuating structure. For example, we have a gallbladder here. Actually, here we have two artifacts. We have acoustic enhancement, which you see as a bright area below the gallbladder, and also a shadow, which is created by a stone in that gallbladder. You can see it in A. We have two artifacts, shadowing from a gallstone and enhancement caused by the low attenuation of the bile in the gallbladder. In B, we still have acoustic enhancement created by bile in the bladder. C, we have enhancement beyond a cervical cyst. Here, beyond the cervical cyst, you see this enhancement. In D, we have other examples. Then we also have this example here. We see enhancement from, I don't know what structure could that be, but it looks like a complex, whatever, maybe a cyst. So you see enhancement beyond, even here. So it's a useful artifact in assessing fluid-filled structures. So uses and potential solutions to shadowing and enhancement. Shadowing and enhancement artifacts are often useful for determining the nature of masses and structures. Shadowing and enhancement are reduced with spatial compounding, as I told you, where several directional approaches to each anatomic site are used to form a final image. The transducer can send beams in different directions to make the beam go around the structure. So this allows the beam to get around the attenuating or enhancing structure. This may be useful with the shadowing because it can uncover structures, especially pathologic ones, that were not imaged because they were located in the shadow before. So the final artifact, we have what we call the focal banding. This is not really an artifact because it is as a result of enhancement in the focal zone. Whenever you focus your beam in an area, that area becomes, its lateral resolution improves. Remember, I told you this. Whenever you focus the beam somewhere, you're trying to improve the lateral resolution, but also the structures in that area becomes more enhanced in brightness. We call that focal banding. We call it focal banding. Brightening of the echoes also can be caused by increased intensity in the focal region of the beam because the beam is narrow there. When you focus the beam somewhere, the beam becomes very narrow and the intensity increases in that area, which results into enhanced brightness. It's very prominent with the linear phased array transducers. So that is what I'm talking about. Here they were using a linear probe, focusing somewhere in the phantom, and you see the enhancement around the focal zone. So focal banding is a brightening of the echoes around the focus, where the intensity is increased by narrowing of the beam. All right, so that marks the end of the beam mode imaging artifacts. The remaining artifacts are for Doppler ultrasound, but these ones, we shall look at them after finishing Doppler ultrasound physics. So next week, we are going to start looking at Doppler ultrasound physics. So encourage your fellows that have not yet paid tuition to pay so that they can come back on the platform and we continue with the Doppler ultrasound. So let me end here. If there is any question, please unmute and ask before we close. Is there any question?
Excuse me, sir.
Yes.
I request that you recap for me about spatial compounding, how spatial compounding help in controlling or preventing these artifacts.
I told you that if you have a structure like this one and you have a transducer, maybe somewhere, I give an example of a linear probe, we expect that this probe sends beams vertically downwards. That's why linear probes, like for example in this image, they form rectangular images because they send beams vertically downwards, forming such an image. But spatial compounding is whereby this transducer is also made to send beams in other directions. You realize that some of the beams can go around the structure. If it was forming a shadow like this one, a shadow like that, these beams, since they are being sent in other directions, they can go around the structure and reveal the structures which were initially in the shadow. They can reveal the beams which were initially in the shadow. So these transducers are sending these beams in other directions to make sure that they go also around this structure is what we call as spatial compounding. Is that clear now?
Yeah, so clear. So what is another way of reducing these artifacts other than spatial compounding?
There's no any other way. Maybe another way, maybe you can scan from another window. For example, if the previous window, the beam was going through a structure which was casting a shadow, if you change it to another window, maybe you may not see it. You may not send the beam through that same structure. Okay? So you can try to avoid the structure which is putting in the shadow. If you're not interested in that structure which is causing a shadow, you may change your window and try to make the beam go through another window where that structure is not that structure is not existing, such that that beam can reach the structures of interest. Maybe you can do that. Okay. Okay, someone is asking about the progressive. Since you have reminded me, I'm also going to inquire from the examinations officer because that exam was already submitted to them. All right. Any other question? Muhimbise Aston, what's your question?
Thank you, sir. So my question was, you said that this beam shadowing, that like this in this type of artifact, it helps to reveal some structures. For example, the if they are like stones, you can easily identify it. Now, if there is spatial compounding, you said that the beams are sent in various directions, and won't they displace like the shadow? Won't it disappear such that you as a sonographer you are incapable of again identifying that particular structure because the shadow has been casted away?
That is what I said, that this artifact is useful. This artifact is useful. If you are assessing stones, why would you use spatial compounding to remove this shadowing? Your interest is stones. You're assessing stones. That implies that this artifact is useful to you. Then why would you use spatial compounding? I have just said that you only use spatial compounding if your interest is not a structure which is putting in the shadow. If your interest is in the structures which are beyond that highly attenuating structure, then you can use spatial compounding to reveal what you want. Have I answered your question?
Yes, sir. Thank you.
Any other person? All right, members, so if there are no more questions, let's end here. Let's meet next week. Tomorrow, I'm not coming for physical class. So let's meet next week on Wednesday online for the BMI DMR group.